Before we talk seriously about threats, controls, or compliance, we have to answer a deceptively simple question. Who exactly are we talking about when we say quantum vendor or developer? This matters more than it sounds. Threat models fail most often not because the threats are misunderstood, but because the scope is fuzzy. People assume this doesn't apply to us, or that's someone else's problem. So this video is about drawing a clean boundary around who this threat model applies to, and just as importantly, who does not apply. So let's start by being precise. This scope is not a lone academic lab doing exploratory research with no external users. It is not a purely theoretical group running simulations only, or it is not a single prototype system operated by one trusted team. The scope is organizations that build, package, operate, or expose quantum technology or quantum enabling software. Organizations that store, process, or monetize quantum-related data or IP. And organizations that interface with customers, partners, or collaborators. So in other words, the moment quantum research becomes a product, a service, a platform, or a shared infrastructure, you are in scope. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On my channel, The AI Law, I unpack how AI security flaws, governance failures, and model behavior turn into real legal exposure, rights issues, and the future of jurisprudence. This distinction is critical. Academic researchers are primarily concerned with correctness of results, novelty, and reproducibility. Vendors and developers must also care about confidentiality, integrity at scale, availability guarantees, legal obligations, and customer trust. The same technique that is harmful in a closed lab becomes risky when automated, exposed through APIs, or reused across multiple devices and customers. This paper describes techniques that vendors will inevitably operationalize. This slide defines what operationalize really means. For this threat model, we consider 5 overlapping categories. Many real organizations fall into more than one. These are organizations that design, fabricate, or operate superconducting qubit systems, trapped ion systems, photonic quantum processors, or hybrid architectures. So why they are in scope? They collect vast amounts of raw telemetry. Their devices have unique proprietary characteristics. Control and calibration directly affect physical systems. Their most valuable IP is often not the chip layout. It is the accumulated operational knowledge embedded in data and models. Category 2, control stack and firmware developers. This includes teams that build pulse-level control software, firmware for control electronics, real-time feedback systems, calibration pipelines. Why are they in scope? Their software directly controls hardware behavior. Errors or manipulation can degrade performance or damage systems. ML-driven automation increasingly lives here. This layer is a control plane. Control planes demand stronger integrity guarantees than ordinary application code. Category 3, quantum software platform providers. These are vendors offering compilers, circuit optimizers, SDKs, transpilers, or workflow orchestration tools. Why they are in scope? They transform user intent into executable operations. AI-generated or AI-optimized outputs may run directly on hardware. They often handle customer IP, circuits, algorithms. They sit in the supply chain between user and hardware. Supply chains are prime attack targets. Category 4, quantum cloud and service providers. This includes any organization that offers quantum access via cloud APIs, schedules jobs, manages multi-tenant environments, or brokers access to partner hardware. So why are they in scope? They aggregate, Customers, data, and execution environments. They must isolate tenants. They are legally accountable for uptime, correctness, and confidentiality. They are infrastructure providers even if the hardware is experimental. Category 5, AI for quantum tool developers. These are teams building ML-based calibration tools, AI decoders for error correction, generative models for circuits, optimization frameworks. Why are they in scope? Their models encode valuable system knowledge. Their artifacts are often reused across devices and customers. They blur the line between software and system behavior. Models become high-value assets and high-risk artifacts. A common objection at this point is, we don't sell this, it's internal tooling. That does not remove you from scope. Internal tools still affect system behavior, create records and artifacts, and influence outcomes customers rely on. So from a security and legal perspective, internal does not mean low risk. Internal often means less audited. Some of the most serious incidents in technology come from internal systems that were never threat modeled because they were not customer facing. Quantum development is highly collaborative. Vendors routinely work with universities, government labs, international partners, hardware suppliers, and customers doing joint research. This introduces cross-border data flows, shared infrastructure, mixed trust boundaries. From a threat model perspective, collaboration expands scope dramatically. Even if you're careful, your collaborators' practices can create exposure for you. Another subtle but important point. When we say developer, we include physicists, research engineers, data scientists, and ML researchers inside vendor organizations. Now you'll ask, why? Because from a risk standpoint, a researcher notebook, a training data set, or an experiment log, they can be just as sensitive as production code. Security and compliance controls must extend into research environments, not stop at the product boundary. To make this conversation concrete, it helps to visualize the quantum vendor stack as layers. Physical layer, qubits, cryogenics, optics, electronics. Control layer, firmware, pulses, timing, feedback loops. Data layer, telemetry, logs, experiment results. ML layer, training pipelines, models, decoders, optimizers. Application layer, compilers, SDKs, customer-facing APIs. And governance layer, access control, logging, compliance, and export restrictions. This threat model applies across all layers. Security failures often occur when responsibility between layers is unclear. Many organizations attempt to scope narrowly. Security owns cloud, engineering owns models, legal owns export controls. That fragmentation is dangerous. The risks described in the research paper as we are discussing emerge between layers. When ML outputs feed control systems, when telemetry feeds trading, and when collaboration feeds datasets. Threat modeling must therefore be cross-functional. To avoid confusion, let's be explicit about what is not covered here. Speculative future cryptanalysis by large-scale quantum computers. Consumer endpoint security. Unrelated AI ethics topics. Purely theoretical quantum algorithms with no operational footprint. Those are important, but they are not the focus of this threat model. This scope is about operational AI for quantum systems. One reason to be disciplined about scope is credibility. When regulators, auditors, or enterprise customers ask, a clear defensible scope shows maturity, prevents overclaiming, and avoids blind spots. So this video gives you the language to say, we have identified where our responsibilities begin and where it ends. So now that we have clearly defined who is in scope, what kinds of systems we are talking about, and why vendors and developers are uniquely exposed, the next question becomes unavoidable. What exactly are the assets within the scope that attackers, competitors, or regulators care about most? The next video will identify those crown jewels, the specific technical and legal assets that anchor the threat model. Everything else flows from that. If you work on AI, security, or law and want to understand what actually gets you sued and what would change, you are in the right place. Subscribe to my channel, The AI Law, and let's meet in the next episode of the series.